So good afternoon, everybody. Welcome to the Joint Astronomical Colloquium in Heidelberg. And this week, we're very pleased to welcome Jonathan Mackey from the Dublin Institute for Advanced Studies. And Jonathan actually is spending some time in the Cologne-Bonn area. And so it's very nice to have him down here to tell us about maybe some topics at the interface between thermal and non-thermal astrophysics. So I'll call on Andreas to give the formal introduction.
Thank you, Richard. Yeah, it's a pleasure to have Jonathan Mackey here. Jonathan started his scientific career with a bachelor in physics and applied mathematics in Galway in Ireland, before then going to the USA to did his master thesis at Harvard at the CFA with Martin White. He then took a career break before re-entering astrophysics and finally finishing his PhD in 2010 at the Dublin Institute for Advanced Studies, DIAS, back in Ireland on the thesis topic of formation and evolution of structures in H2 regions. In hindsight, a study that, yeah, okay. Thanks. In hindsight, a study that set him on his now well-developed career path. So that was with Andrew J. Lim at that time. He then went to what Richard already introduced to Bonn as a postdoctoral researcher to work with Professor Norbert Lange and his group. First as an Agelander Fellow and then as an Alexander von Humboldt Fellow, right? In 2015, he was a postdoctoral fellow at the University of Cologne in the group of Professor Stefanie Walch before shortly after going back to DIAS, this time as a Royal Society University Research Fellow, one of the most prestigious research fellowships that you can actually get in the UK and Ireland, and he got the Irish one, obviously. So then, since then, he's at DIAS near Dublin, and has built up a research group focused mainly on high energy astrophysics and computational astrophysics and massive stars. And Jonathan will now show us what he's currently up to and some of the highlights he has worked on in the past. Take it away, Jonathan.
Great. Okay, thanks very much, Andreas and Richard, for the invitation and for the welcome and for inviting me to give this colloquium. Great to be here. Good to see everyone here. Yeah, so I apologize for the title. It seemed like a good idea at the time, but now that I read it, it seems pretty dry. Radiation from shock plasma around single and binary massive stars. So, yeah, good. So the outline of the talk, I will give a quick sort of introduction to shockwaves and hot phase of the interstellar medium and to bow shocks of massive stars. Then I will go into some numerical modeling of bow shocks and what we can potentially learn from this. And then kind of related to bow shocks are these colliding wind binary systems, where instead of just the stellar wind interacting with the interstellar medium, you have two stellar winds interacting with each other, but you have basically the same shock structures forming, just millions of times brighter because the length scales are so much shorter. Time scales are also orders of magnitude shorter. And then if I have time, although I think I was a bit over optimistic with the abstract, I'll do a quick excursion into high energy astrophysics, which has been the last few years of my career, in parallel with this other work, and then a summary. So we see how far we get. I'll keep an eye on the clock. So I was asked to give a sort of a quick introduction as well to the topic, like a sort of basic introduction. This is a sort of a cartoon overlaid on a computer simulation of a colliding wind binary system, where you have two stars and a stellar wind expanding in all directions from each star. This star has got a weak wind. This star has got a very strong wind, a denser wind, and what you get is, because these winds are hypersonic, you get strong shocks forming. Here is the contact discontinuity between the two, where basically the interface between the two winds, and then you get reflected shocks on both sides that typically have very high Mach number, high alpha in Mach number. And because this star is a weaker wind, the momentum balance says that this will form a bow shape. And in these shocks, you can get particle acceleration. In fact, you will pretty much ubiquitously get particle acceleration. And so the thermal particles get scattered up to higher energies and eventually get to relativistic energies, and until basically they're so high energy that they escape the system or they interact with something and radiate gamma rays. And in these systems, you can get gas heated to like 100 million Kelvin. More typically something like 10 million, but you can get really hot plasma in these systems. So here are a few examples of bow shocks of hot stars. So these are, we think, all of these are single stars. All of them are runaway stars, which means they probably at some point were binary stars. And then one of the stars exploded, and the other one, well, when one star explodes, this removes a lot of mass from the binary system. And if you remove enough mass, then the binary system becomes unbound. And the star that was originally flying around in the binary orbit just starts going in a straight line.
Yeah, these are pretty famous examples. So this is called the Bubble Nebula, NGC 7635. So this star here is moving this direction at about 30 kilometers a second into quite a dense medium. And you see this bow-shaped structure out here, and then also this bubble structure here forming around it. And so both of these are formed by shocks. And they're just different tracers. This is a like oxygen spectral line, and this I think is a nitrogen spectral line producing this. In this case, Zeta Ophiuchi, this is the closest O star to the Earth. So it's only 135 parsecs away from us. And it's producing this spectacular bow shock, which is seen here in infrared data from, I think, the Spitzer Space Telescope. So it's also moving this way, about 30 kilometers a second, to fairly dense medium. And yeah, it has a much weaker wind than this one because it's a lower mass star, but much closer to us, and therefore we can potentially get a lot more information by spatially resolving and being more sensitive to radiation from different wavelengths. BD +43 3654. So this is a like 60 to 70 solar mass star, so it's a very massive star that was ejected from the Cygnus OB association and is moving out of the Cygnus region.
Yeah, this is again an infrared image. This is much further away from us. It's about 2 kiloparsecs away. But because of the mass of the star, it has a very high mass loss rate and quite a fast wind. So this is actually maybe an order of magnitude bigger in physical size than this one. Yeah, so I come back to these in a few minutes. From these infrared images, actually, it's not often clear where the shocks are and what these discontinuities are that you are seeing. So that's something to come back to. You can actually see these in radio. This is from the PhD work of Maria Muzzori, who was in my group. Started off doing computer simulations, realized that she hated it, but really liked radio astronomy. So I've supervised a radio astronomy PhD with some help from people in Bonn and in Mexico. And we applied for, got VLA data, and measured these, detected these bow shocks of this. This one is BD +43, this one, and the Bubble Nebula. Should have put them opposite each other. This one is the Bubble Nebula. So these contours that you see are the VLA images that we obtained. You see the structure, and these blue contours then are the infrared intensity contours. This one is not so well resolved in infrared, but you can see that the structure is quite different in radio. And actually, when we measured the spectral index of the emission, this here is thermal emission because it corresponds to basically this bright rim cloud here. So this is just free emission from this photo evaporating cloud. But the rest of it, so from here, and so basically from here, this and this are the apparently synchrotron emission. There are some difficulties with being sure that it's synchrotron emission with extended emission with a radio interferometer because you're missing some of the flux. basically your sensitivity to scale, different scales, is a function of frequency. But it looks like these are both synchrotron emitting, which tells you also that there is particle acceleration happening in these shocks. So a very quick introduction to shocks. So most of you will have seen most of this before. We start off with the conservation equation. So if you just consider the conservation of mass, momentum, and energy, you can come out with these relations known as the Rankine-Hugoniot conditions for shocks. This is for conservation of mass, conservation of energy, or momentum and energy. And if you set the adiabatic index to 5/3, which is pretty much always a good good approximation for fast shocks with ionized plasma, then you come out with these values. So the shock jump will be a factor of 4. The velocity will decrease by a factor of 4 across the shock. And the temperature that you get in the post-shock region only depends on the shock speed for high Mach number shocks. And put this in numbers, if you have a shock of about 1,000 kilometers a second, you get a temperature of about 1 keV. So this is X-ray emitting plasma. Put in this picture of the Cathay supernova remnant because I think it's absolutely spectacular. I wasn't involved in this work at all, but you can see really beautiful shock waves here in this infrared image. And actually, with the high resolution of JWST, you can see that basically the shock structures are way more complicated than what we could see before. When you add magnetic fields to this picture, it gets a little bit more complicated, but not very much. So the magnetic flux should also be conserved. So the flux parallel to the shock normal is completely unchanged, but the magnetic field perpendicular to the shock, so aligned with the surface of the shock, gets compressed in the same way as the gas compression ratio. So in a strong shock, this will be a factor of 4. In a situation where you have radiative cooling, the cooling time is in principle a function of density, temperature, and composition, so hydrogen, helium, and metal abundance. But in general, mostly it's proportional to the abundance of heavy elements and scales as 1 over the density. And the temperature dependence is much more complicated because of basically the different coolants that you get at different temperature. But if the shock is radiative, so if the cooling time is shorter than the dynamical time scale, you lose pressure support, you get further compression, and this is the isothermal limit. So basically the compression factor, the Mach number squared times the initial density, and velocity, the inverse of that, and same with the magnetic field. But if you look at this is actually not always possible. So if you have, say, a Mach 100 shock, in theory, you can get a compression factor of 10,000. But if you look at how these things scale, so the magnetic pressure can't be radiated away. Once you compress the magnetic field sufficiently that it's actually dominating the total pressure, then you basically cannot get any more compression. And if you just put in how these scale with the Mach number, this term here scales with the Mach number to the power of 4, and the other scale with a much weaker power of Mach number. So quite often, if you have radiative shocks, the post-shock plasma will become magnetically dominated. And you can get very high magnetic fields, which you don't typically get in the interstellar medium. So going to stellar wind bubbles, a little bit of history. So this paper by Matthews in 1966 looked at the Rosette Nebula, which has got a bunch of massive stars in the center. And it's got this basically cavity here surrounded by photoionized gas emitting brightly in H-alpha recombination radiation. And the point of this paper was to suggest that the strong winds that had just been detected in spectroscopy from these stars, that the dynamical pressure of the winds basically was what was creating this cavity, and that was then creating this discontinuity here between the wind material, the shocked wind, and the interstellar medium. the idea was that this should then be a hot plasma. This was then developed in the next few years. So this figure from Dyson and de Vries in 1972, where you have the freely expanding stellar wind. Then you have the termination shock of the wind, where and the contact discontinuity here. So this is a reflected shock from the interaction with the interstellar medium. And then you can have a forward shock from the basically expanding into the interstellar medium. And if you calculate what the bubble size is from a dimensional analysis, if this shocked stellar wind region is adiabatic, so basically doesn't lose energy, either cooling or mixing or any think terms for energy are not efficient, then it will expand quite fast, well, with this t to the 3/5 power. And in the radiative limit, you get t to the 1/2. This actually makes quite a big difference if you look at feedback from stellar winds to the interstellar medium. If you are in this adiabatic limit, then stellar winds can be quite an important component of the feedback to the interstellar medium in galaxies, for example, driving turbulence and contributing generally to the turbulent energy that's in the interstellar medium. If you're in this radiative limit, so there's just a momentum-driven limit, there's really not that much energy from these stellar winds in comparison with other processes into the interstellar medium. So one of the important questions in interstellar medium physics at the moment is which of these limits are we closer to? The consensus seems to be more that we're closer to this than to this, although this probably depends on scale. And then if we're close to the radiative limit, how does the energy get lost? We know that this hot phase is there because we've been able to detect it, mainly from Chandra and XMM over the last 20 years. So there's this really nice paper by Townsley et al. 2018, where they look at many star clusters and associations in the galaxy. I took here the example of the Rosette Nebula. So there's a lot of point sources, obviously, but there's also this diffuse X-ray emission coming from the center of the Rosette Nebula, and this fills the cavity that you see in the optical emission. So the X-rays are basically our only diagnostic of this hot phase of the interstellar medium. The density is very low. It's very hard to measure it in any other wavelength in terms of thermal emission. It quite often emits synchrotron radiation because you can have high energy particles and reasonably strong magnetic fields. But the emission measure of the plasma is so low that it's very difficult to detect at any other wavelength. But we know it takes a significant fraction of the interstellar medium volume. With some review papers on this from the last 20 years. We know kind of what the sources are. So supernovae, stellar winds, combined stellar winds and supernovae from star clusters, compact objects emitting basically there's a lot of energy coming out of these that can contribute to the hot phase of the interstellar medium. And we know pretty much what the sinks are. So once it's overpressured, it will expand through adiabatic expansion and it will cool down this way. Radiative cooling, if the density is high enough, but typically if you calculate the cooling timescale of this plasma, it will be like billions of years because the temperature is so high, the density is so low. And the only efficient coolant is really Bremsstrahlung or inverse-Compton cooling off the CMB. So yeah, inverse-Compton cooling. You can have thermal conduction and something called turbulent mixing, which is a bit of a often not very well-defined phase, but basically thermal conduction is you have this hot gas. The electrons in here have a kind of quite a large mean free path because they're hot. They penetrate a little bit across the contact discontinuity into the colder phase and basically take some energy out. And this then is a diffusive process that smears out this boundary and creates a sort of higher density, lower temperature region that will then radiate very efficiently, and you lose a lot of energy that way. So at the surface of this bubble, turbulent mixing is in some ways kind of similar because these two regions, the hot and the warm phase, have very different sound speeds. There's typically a shear flow along here, so you can get Kelvin-Helmholtz instability, which will then entrain some of the cold material or cooler gas into the hot phase. Again, you create intermediate temperature gas that will cool very quickly. if it's accelerating, you can also get Rayleigh-Taylor instability, things like this, which will do a similar thing. So the question is then, what's the relative importance of different processes on different scales? And in order to understand this hot phase of the interstellar medium, we really need to know which are the main cooling processes and what's the relative importance of all of these in different types of galaxies, different parts of the interstellar medium. For example, the galactic center is totally different to the solar neighborhood. There are some measurements of this looking at particularly at stellar winds. So Anna Rosen in 2014 looked at massive star-forming regions in some in the galaxy and also 30 Doradus, and looked at basically what is the wind input power and where do we see this energy in basically radiative cooling, mechanical energy, so the expansion of a bubble around the region, thermal conduction, emission from dust. And basically the conclusion is that most of the energy is unaccounted for, in pretty much all of these regions. So it's either lost through leakage of bubbles, or there is something like thermal conduction or turbulent mixing that is very effectively removing energy from the interior, from the surface of the hot phase. This has been looked at a little bit, so I really like this paper by Lancaster et al. In 2021. There's like papers, one theory and one simulations, where they're looking at the difference between a stellar wind bubble expanding in a uniform medium and expanding in a fractal medium in this case. So it was static, but it had a structure. And they find that the fact that this medium has a much larger surface area, or the bubble expanding in a fractal medium has a much larger surface area to volume ratio compared to here. And the fact that it's not spherically symmetric, so you get a lot of flows in different directions. This means that in a medium like this, you lose energy much more efficiently than in a medium like this. And that the stellar winds, they're arguing that they're basically are closer to the momentum-driven limit rather than the adiabatic stellar wind bubbles. But I think this is not completely settled, and it's not clear how this applies in different scales and different types of medium. In particular, so bow shocks, these are analogs of the heliosphere around massive stars. So, and in general, the wind bubbles that we see very few spherical wind bubbles. So the bubble nebula is almost unique in that there is a circular bubble around the star, even though the star is not at the center. So we know we have a turbulent interstellar medium. There are quite large density fluctuations in the interstellar medium on a range of scales. The stars are often moving. You have interactions with nearby stars. And as I said, the bubbles themselves are very hard to see because the emission measure is so low. So if you have stars moving through the low density interstellar medium, there's a number of advantages. So one, shock compression, the star is moving, so this outer shock compressing the interstellar medium is often a radiative shock, can give you quite large compression factors. This is quite easy to detect. You're quite often in a lower density, so diffuse interstellar medium, which has got less structure on small scales. So it's simpler to model. And also, sometimes they're going out of the galactic plane, so you have less source confusion. It's much easier to see what's going on. The characteristic size of these you can get from the basically pressure balance, balancing the ram pressure of the stellar wind with the dynamical pressure of the interstellar medium through the relative velocity. And you get a term like this. So basically a stronger wind gives you a bigger bow shock. A denser ISM or a faster moving star compresses it. Yeah, this is one of the original references. Very hard to find online, but you could find. So if the star is moving, you basically have the same structure as I showed before, except it's asymmetric in this case. So how do we model this? Generally, You can do quite a bit with analytic calculations, but if you want to look at things like turbulent mixing or instabilities, you need then to go to hydrodynamics. The simplest way to do this is using the finite difference or finite volume method. So you have these conservation laws for mass conservation and momentum conservation, and you study basically in this case a grid-based code. You look at how much stuff is flowing in or and out of the interfaces to the cell in each time step, and you're basically just conserving mass, conserving momentum, conserving energy through each cell, and then integrating these equations according to that. So you're turning these basically calculus into algebra. And computers are excellent at doing algebra, as we know. So yeah, so this is what we do. This has been very well developed for 50 years now. I, for my sins, wrote one of these codes during my PhD. I didn't know at the beginning of my PhD I was going to write this code. I was supposed to inherit Andy Lim's code, but he never gave it to me in the end because he couldn't remember how the algorithms worked. Or at least that was what he told me. So in the end, I wrote my own code. I don't know if I would do this again, but yeah, I learned a lot. So it can do quite a lot at this stage. So 1D, 2D, and 3D simulations, solving Euler or ideal MHD equations, and it can work with a statically nested grid like this, which is quite good for solving problems like this, where you know in advance where you're going to need the high resolution, or for binary systems where you know basically where the shocks are going to be at any point in the orbit, so you can focus the resolution there. Yeah. So in the last few years, we added some capabilities for basically modeling binary systems. So looking at moving stars, so added basically an n-body integrator to calculate the positions of the stars, adding in wind acceleration so that we can model basically the winds accelerating away from the star, because in these binary systems, the shocks actually get within a few stellar radii, so you're quite deep in the acceleration zone of the wind. And we dramatically improved the parallelization of the code so that it runs much better on large computers. So this is an example of the scaling that we're getting now on a problem very like this one, where we have basically static mesh refinement zooming in on the two stars, and we're looking at this structure that forms as the stars go through periastron. And going from 128 up to 8,000 cores, so a factor of 64, I think, the code basically stays 50% efficient solving the same problem. So this is pretty good and that's basically with this OpenMP hybrid MPI OpenMPI parallelization. So at the moment we're looking into adding some GPU parallelization. This is quite difficult though. It's quite new for me, so I have some summer students who are going to teach me how to do GPU coding, and hopefully we get this working soon. Okay, so some computer modeling of basically bow shocks, shock stellar winds. So from some of these papers, these results I'm going to show. I'm going to start with Zeta Ophiuchi. It's only, as I said, closest O star, only 135 parsecs from Earth. And it's at galactic latitude plus 25, which means way out of the galactic plane, because we have a super clear view of it. The star itself is really well studied because basically spectroscopists have looked at this star ever since we've had spectrographs. There's quite a lot of interesting stuff along the line of sight. And this is an image of the Spitzer Space Telescope data that you saw before, but also there's Chandra data in blue. You maybe can see that there is actually some diffuse emission here. This is a press release from a paper by my student Sam Green for his computer modeling. And we were trying to model basically this diffuse emission from Chandra. This was first detected by Toala et al. In 2016. Here's their image of the diffuse X-rays in the color where it's easier to see, with contours of the infrared emission from the bow shock. So we reanalyzed this, basically confirming this detection. It's a pretty difficult thing to detect because this sort of yellow stuff here is pileup from the star. The star is quite a bright X-ray source. So I think I have an X-ray image somewhere. This was our X-ray image with the star subtracted. But basically all of this we think is still severely contaminated by the star. But this then is the 3 sigma contour of the diffuse emission that we derived. And so basically everything outside of here we think is the diffuse emission from the hot shock plasma. So Sam did these simulations. They were actually the first 3D MHD simulations of this bow shock, first 3D simulations at all, trying to model this bow shock. So taking the mass loss rates that we know, the wind velocity, the conditions in the interstellar medium. So we looked at the X-ray emission that we get. This is what it is. So it actually looks qualitatively quite different from the observations, which was disappointing. This is overlaid the X-ray on top of the infrared emission, synthetic infrared emission from the simulation. So the infrared emission matches the observations reasonably well. This is basically an animation of the simulation, going from the initial state to basically a relaxed state where it's reached an equilibrium. You can see there's basically no instabilities here, which we'll come back to in a few minutes. So from the simulation, we calculated the X-ray emission as a function of time. This gray band, basically what we derive from this diffuse X-ray emission. And this dashed line is what we get from the whole simulation. So actually a much larger region than here because it extends way down into the wake behind the star. And this is from just within, I think, 0.25 parsec radius of the star. So we're actually quite far below the observed value. And we were expecting, if anything, to be above the value, because if the resolution is too low, typically you have too much numeric diffusion in the simulation. And this then basically gives you quite a thick mixing layer of gas that emits quite strongly in X-rays. So we wanted to look into that by doing a resolution study. So we, first of all, so in Sam's work, we were using this HLL Riemann solver, which those of you who know, this is very diffusive. It cannot resolve contact discontinuities very well, but it's super robust, which is why we used it. It doesn't break. So we upgraded to a hybrid HLLD solver, which has got a contact discontinuity and is much more accurate. And we went to higher resolution, 2D and 3D simulations. You can see, so this is a 2D simulation with a similar resolution to Sam's 3D simulations. You see it's relatively smooth. There's still a little bit of structure forming. But if you go to much higher resolution, so basically 4 times higher in each dimension, then you see there's a huge amount of mixing going on from Kelvin-Helmholtz instability that's driven by the shear flow. So this hot gas that has got like 1,000 kilometers a second sound speed expanding like this, and then the cooler gas, which has a 10 kilometer per second sound speed, is advecting in this direction at basically the velocity that the star is moving, so 30 kilometers a second. So there's a very strong shear here. And what we found is that once you have the resolution to resolve this, the X-ray emission gets really much more variable. So this is from the 3D simulations as a function of resolution. Let me see. Yeah. So this is the one where the magnetic field ISM magnetic field is perpendicular to the velocity of the star. And basically at low resolution, we don't get very much fluctuation. It's this blue one, but if you look at the red dashed line, we're starting to get a little more. And then if we go to higher resolution again, you're getting actually almost order of magnitude variation in the X-ray luminosity. And you can track this to the formation of these Kelvin-Helmholtz instabilities in the wake behind the star. If the magnetic field is parallel to the velocity, then things are much more unstable, even at low resolution, which is another interesting thing. And then if you look at these are basically the highest resolution 3D simulations that we could run. You can see there's a lot of substructure here, there's a lot of mixing going on here. And this material is what's emitting the X-rays. And if you look at the X-ray emission maps that you get, so as a function of time, once the initial conditions are gone, you see that sometimes there's actually a lot of emission from the wake behind the star. Sometimes there's very little. And then it basically, this is just two different projections of the same simulation. Yeah. So I guess what we kind of learned from this is that getting a snapshot of the X-ray emission in time, it tells you something about the hot gas content of the hot bubble, but it doesn't necessarily, what you can infer from this is maybe quite limited unless you have a statistical sample of these objects, because the time variation is so large. So we're also working on part of the motivation for doing MHD was that we can then look at synchrotron emission, because we have the magnetic field orientation and field strength. So we're working on that at the moment. I hoped I'd have something to show, but I don't quite yet. But I think before the end of the summer, that should be ready. Okay. So looking at these bow shocks, the X-ray emission, people often use this to quantify radiative cooling in wind bubbles. What we found is that this actually doesn't really work because the emission is so variable, that if you can actually resolve this mixing that should be occurring at the interface from these shear flows, then it will vary by like a factor of 10 over time. It's also very weak, so it's less than 0.1% of the input energy. So you're yeah, you can actually, what we saw in the simulation was that this mixing sometimes cools gas directly from the hot phase into that it's not going to be emitting X-rays at all. It's going to be in the UV emitting range, so like 10 to the 5 to 10 to the 6 Kelvin. Even still, so numerical convergence is an issue. We can't actually do this. The 3D simulations at as high resolution as we would like, especially compared to the 2D. So I think in this case, higher order methods would actually be useful. And I think adaptive mesh refinement would be pretty useful here, I think, because we're just trying to resolve a surface here. We're not trying to resolve the whole volume. So I think in this case, the adaptive mesh refinement would be much more useful. Okay, so that's that. So colliding wind binaries, I guess it took longer than I thought, as I expected. I won't have as much time as I thought. So the binaries are, as I said, kind of like bow shocks. You can use them to probe the winds of the stars. You can, if they have eccentric orbits, and quite a few of them do, you have these predictable time-varying shock conditions. So you can constrain some of the physics of the winds of massive stars. So wind clumping, acceleration of the wind, mass loss rates. They're also intense dust producers quite often, some of these colliding wind binaries. And there's the strong particle acceleration that you can see. So for example, this is WR140. It looks like a cartoon, but this is 3 radio observations superposed on a cartoon of the orbit. And this is synchrotron radio observations from Doherty et al. 2006. And this is basically the shocked region where the two plasmas are colliding. This is a fantastic image of the dust in this system. So the binary is somewhere in here, and each orbit, WR140, produces a lot of dust for a very short time around periastron. And these concentric rings are basically concentric periastron passages of the system. And in this, I think you can see like something like 15 or 16 of these periastron passages. Up to before this, you could only see, I think, 2 of them. We have actually excellent X-ray data, WR140. It's because it's super bright. And it has a long period, so it's about nearly 8 years. And so over the last 20 years or so, we've got 3 orbits or 3 periastron passages. And you can see it follows this dashed line pretty well for most of the orbit. This dashed line is what you get if you have an adiabatic shock. And basically, you just measure the volume and the density that you have in the X-ray emitting region. And this is what you should get. But around periastron, it deviates quite strongly from this. And there's a very big dip at periastron. And then it recovers afterwards, but not quite to the adiabatic limit. And then it slowly goes back to the adiabatic limit. And we've seen this repeating now 3 times. It's coming up again in November. And it's pretty clear that this collapse in the X-ray emission creates the conditions for dust formation. Basically, to form dust, you need gas that's like 1500 Kelvin or lower to have a lot of carbon in it, and it should be shielded from ionizing radiation. So, yeah. So we wanted to try modeling this. This is the orbit of the 2 stars, and this is the mesh that we have with a couple of the finer or the coarser levels put out. We started like 140 days before periastron and went through periastron and finished about the same time afterwards. So the sort of novel thing of this simulation was that we included inverse-Compton cooling of the thermal electrons. This was actually, I thought it was completely novel, but then I found this paper from 1976, where this guy had calculated it should be important. Also this paper from the 1990s. But basically for the past 30 years, nobody has included this in any of the models. The idea is that if the shock is really close to one of the stars, the radiation field is so strong that even though it's non-relativistic plasma, so calculate the cooling rate, it basically depends on the radiation field, the radiation energy density. And the cooling time only depends on constants and the radiation energy density. So if this cooling time is shorter than the time that it takes the plasma to go from here, the apex of the shock down here, then this should be an important process. So, and basically we showed this with some analytic calculations and with this setup here where we ran a simulation with this inverse-Compton cooling and without. And you can see that in this case, the shock stays basically adiabatic. And in this case, it becomes radiative and becomes quite unstable. So you can get a qualitative difference in this case. This is the simulation going through periastron. And you can see for a very short time around periastron, the shock becomes radiative due to this inverse-Compton cooling. So the inverse-Compton cooling cools down the plasma enough, and this increases the density as well, so that the collisional cooling at some point can take over, and this cools you all the way down then to about 10 to the 4 Kelvin. And then the idea is that in these shocked, unstable regions that are able to cool to very high densities, this is where the gas will become self-shielding, and this is where the dust will form. This is a synthetic X-ray emission map from the basically going through the periastron. If you had an X-ray telescope with incredibly high spatial resolution, you could observe this. Actually, we just get light curves and spectra. So this is the light curves that we have compared to the observed light curve. These are 3 different simulations. This was when we just injected the 2 winds at the terminal velocity, and we just considered collisional cooling processes. Here we included wind acceleration. So basically towards periastron, once you're in the acceleration, the wind acceleration zone, the flow of gas through the shock has lower velocity, so the temperature is lower, so the hard X-ray emission is weaker. And then this one is when we turn on the inverse-Compton cooling, and this is what triggers the shock plasma to become radiative and undergo runaway cooling. So you can see qualitatively we've got pretty good agreement with the observations. Quantitatively, the dip is not quite deep enough and also not quite wide enough. But actually, if you do a slightly lower resolution simulation, this dip is shallower again. So I think this is partly a resolution issue. At the moment, we're trying to run higher resolution simulations to see if we can actually get a converged solution. If you look at the magnetic field, we just put in some typical, well, okay, so most of these O stars don't have measured magnetic fields, and Wolf-Rayet A stars, I think none of them have measured magnetic fields. So we put in something reasonable so that the alpha and Mach number of the wind is relatively large, but not enormous. And basically see what happens. And then we wanted to ask, what's the magnetic field configuration of the shocks? And this is important because basically the angle that the magnetic field makes to the shock normal has quite an important effect on the particle acceleration, according to some plasma simulations. So this is my first attempt at plotting this. I haven't quite figured out how to get matplotlib to do these streamlines. So I did this with Visit. So first of all, the color scale plots V.B. So blue is aligned with basically V and B are aligned. Red, they're anti-aligned. And if it's white, they're basically perpendicular. You can see for the O star, you have this basically Parker spiral. So because the star is rotating and the star is really small, the field is basically a toroidal field at all radii that we can see here. And then for the O star, it's bigger and the acceleration is slower. So we get, you can see it's partly toroidal, partly radial. And what's interesting here is that in both sides of the shock here, basically the field is going at different directions on either side of the contact discontinuity. So you have a strong current sheet at the contact discontinuity. This is, I think, should be pretty general because by and large, both stars have the same rotation axis as the orbital system. Basically, their angular momentum vector points in a similar direction. And so in that case, the winding of the field that you get means that there should be pretty strong current sheet here. And if you look at the angle between the magnetic field and the shock normal, at the apex here, it's pretty much perpendicular, but here it's basically parallel, and here it's sort of mixed. And in this case, here you have basically the field lines are parallel to the surface of the shock, so perpendicular shock, and here is parallel. So I think this will be quite interesting to look at in the context of particle acceleration models. At periastron, it's actually much more complicated because you have all these instabilities, but still the general picture holds that you do have this current sheet that's broken up by the instabilities, but it's still there. And at the apex here, you have perpendicular shock, and then off to the sides, you get more parallel shocks. And plotting here the plasma beta, so the ratio of the thermal pressure to magnetic pressure. The red regions here are magnetically dominated, and the blue are thermal pressure dominated. And you can see that where the shock has become radiative, you get this strong compression of the perpendicular component of the field, and you're getting basically magnetically dominated regions. So this actually tells us that even though MHD simulations are harder than hydro, you can actually, they have the advantage in that in theory, we may be able to spatially resolve the maximum compression factor that you can get in these shock regions. Yeah, so quick summary of this. So 3D MHD simulations, I mean, we have some quite simplifying assumptions for wind acceleration, and actually doing full 3D radiation MHD is quite a few years away yet. Just even doing this for single stars, studying wind acceleration on a small patch of the surface of the star is still very challenging. But it looks like we can reasonably accurately model the thermal plasma for the first time with high resolution. We can predict this magnetic field orientation of the shock, and yeah, working on the X-ray emission to see if we can actually get convergence there. And then basically we can use this as a basis to then test these one-zone and multi-zone models that exist for particle acceleration in colliding wind binaries. This is quite important, I think, because so far only two colliding wind binary systems have been detected in gamma rays, Eta Carina and Gamma Velorum. And we expect that CT should actually detect quite a few more of these, because we get an order of magnitude more sensitivity. We've already got two. The others are not, well, there should be quite a lot more coming over the next 10 years. I'm going to skip this because I've run out of time. Anyway, lots of plasma effects in shocks that probably heard about from some other people in previous talks. Or, this is me at the Hess telescopes. I do want to say, since I'm in Heidelberg, that it's been brilliant for DIAS to be part of the Hess collaboration over the past 20 years. It was originally led by Rory and Felix Aharonian. When Luke retired, I got the opportunity to jump in and took this. It's been great to learn about high energy astrophysics. And actually in Ireland, it's really hard to get funding for infrastructure, hard to get funding for even membership fees for infrastructure. So the model of Hess has been really good for us. That I mean, we've been a very small part of the collaboration. We didn't build any of the telescopes or really give any money to the instrumentation. But yeah, I want to say thank you to the Hess people for including us in the collaboration, because this has taken my career in a lot of directions that I didn't intend and don't have time to talk about. So I have to skip through all of this stuff, unfortunately. Very sorry about that. And I'll leave that there and I'll stop. Thank you very much.
Well, thank you very much, Jonathan. I mean, it's very obvious that those sources are sort of very nice laboratories. And I think it's very true what you say, you know, that with Hess and in the CTA in the future, those sort of laboratories are going to be the place to really test fundamental microscopic processes in high-energy astrophysics.
Yeah, so I didn't say that, but I think like Zeta Ophiuchi, it's big enough on the sky that a Cherenkov telescope could actually resolve the gamma ray emission from the system, and it's very close. And I guess it should be a target for CTA.
Yeah, I mean, especially those nearby objects. Well, now, I'm sure that we have some questions. People online, please put your hand up and type in that you want to ask a question if you want to do so. And I think it was just the first question here.
Hi, thank you. I want to know how well you know the parameters of your simulations. In the end, you want to fit sources, but how well do you know the magnetic field, the mass fluxes, densities, and so on?
Yeah, that's a very good question. So I was talking to Andreas about this before lunch, specifically for this WR140 system. How well do we know the mass loss rates of the two stars? Actually, possibly the best constraints come from the X-ray emission from the wind collision region, far from the periastron. You can kind of measure the mass loss rates from the spectra, but there are uncertainties associated to wind clumping, for example. And especially for the O star, which has much weaker wind, it's quite difficult to extract accurate values of the mass loss rate of the star from the spectrum. So there are quite significant uncertainties. The velocities of the winds are pretty well constrained from the width of the spectral lines. And the orbits are also very well constrained now, because with the optical interferometers, we can resolve the orbits. Yeah, so, yeah, the magnetic fields of massive stars is a very difficult question. So there are some stars, like about 10% of the massive stars have got kilogauss magnetic fields, and you can see they have a magnetosphere. There's very strong X-ray emission because the magnetic field is inhibiting the expansion of the wind and driving collisions in the plasma. But for all of the rest of the stars, no idea. So I mean, I put in it's clear that the wind is super alphanic, so the magnetic field, the surface magnetic field, is not enough to change the flow of the wind from being a spherical outflow. But what exactly the magnetic field strength is not clear.
Okay, thank you. Another question?
Thank you, Jonathan, for a very nice talk. I have a question with regards to your colliding wind binary simulations. You had an interesting idea about EC cooling, which is external Compton cooling, and you mentioned that the photons would have very high temperature while the electrons would have lower temperature, lower energy. So in this case, wouldn't the photon energy be larger than the electron energy, and would it be okay to use Thomson scattering approximation, or would you be going to Klein-Nishina approximation where you want to basically do
so in this case, the shock plasma has got sort of keV energies, and the radiation field has got like a few eV energies. So the radiation field is lower energy. And yeah, I mean, yeah, I think the Thomson cross section is fine.
Okay.
And we looked at the.
Okay, yeah, that's fine. So I just wanted to have another question. I mean, when you showed the hydro simulations of your colliding with binaries, when the periastron, the star came, you generated instabilities. What actually, and then it vanished, the instabilities. What causes the instabilities to vanish? I mean, it completely smoothens out. Why does it happen?
So I mean, it's partly because we put in these nice spherically symmetric smooth flows coming out of the star. And once the cooling time becomes longer than the escape time of the gas from the system, the shocks become adiabatic, and this stabilizes them. I mean, for stars that have different wind velocity, in this case, the two stars have basically the same wind velocity. So there's very little shear at the contact discontinuity. If the shocks are adiabatic, this shear at the contact discontinuity is the only thing that can really give you instability. And people have looked at, so if you put some clumps in the wind, what will that do? And actually, it doesn't really affect the structure. I mean, if they're big enough, obviously it will affect the structure of the shocks. But if they evaporate after being shocked on a timescale shorter than the advection timescale, then the shock still stays pretty stable.
Thank you. Thank you so much.
The back.
Thank you for this nice talk. A question about, maybe a naive question about the evolution of colliding wind binary systems. As you said, they are very interesting progenitors, maybe for compact object mergers. And so my question would be, would this colliding wind also affect the evolution of the orbit?
This is a good question, and it's not. I mean, obviously, the winds themselves, you're losing mass from the system, so this changes the orbit. But there are models where if something special happens at periastron, and you can either have mass transfer or have enhanced winds because of basically tides, and this mass gets lost from the system, then you can actually pump the eccentricity of the system that way. That's thought to be, I mean, it's actually really weird that WR140 has got a highly eccentric orbit, because generally you would expect that a system, it's very hard to understand how this eccentricity arose. So one of the ideas is that basically when one of the stars was a red supergiant, for example, and the outer layers were very poorly bound, that at periastron passage, the tides basically increase the mass loss from the star, and if you do this repeatedly every periastron passage, you lose a little bit of mass. You can mathematically show that this will actually pump the eccentricity of the system.
And would that make it more likely for them to merge?
Could do. Yeah, I mean, if you ask Nathan Smith or Philip Podolsky with regard to Eta Carina, they will say that that's how the great eruption in Eta Carina happened, that something was pumping the eccentricity of a binary, and that merged, and the binary that we see now is the remnants of a triple system. So I think it's possible. I mean,
Thank you.
Okay. Oh, one more question.
So going back to the 3D simulation of the colliding winds, you partially addressed this while answering Christian, I guess, but what was the initial, the choice for the initial configuration of the magnetic field, and why? Because it looked like one of the stars had a toroidal field, but the other one was like radial, or what was the?
No, well, so both of the stars have a radial field at the surface of the star. But because the Wolf-Rayet star is much smaller, you can't actually see the part of the domain where the wind is radial. So basically the radius at which the wind becomes toroidal is much smaller for the case of the Wolf-Rayet star. No, it's the same. So we actually don't also know what the rotation rate of these stars is, because the spectral lines are pretty broad from the Wolf-Rayet. And that's another uncertainty. So I just took 100 kilometers a second rotation speed for both of them and picked magnetic fields so that the alpha in Mach number is like a few tens.
Okay, I think we'll have to draw a line here. It's now just 5 minutes past the time, and I don't see any online questions. Before we thank Jonathan, I just have a couple of announcements to make, if I can put that up on the screen. The first of which is that immediately afterwards, we will be going to, yes, well, immediately afterwards, we'll be going to Hemingway's for a dedicated meeting for students and postdocs. So if you want to do that, could you please announce yourself at the front of the lecture theatre after the talk? And I think the previous slide shows next week's talk, where we are going to hear about white dwarf supernovae from Robert Fisher, who is presently visiting here in Heidelberg. So if you want to prepare for that, or even talk to Robert in advance or afterwards, he's around in Heidelberg. So with that, it's just up to us to thank you very much again for Jonathan for coming and giving this talk, also at very short notice. And I think you've shown very, very nicely, at least I learned a lot about these processes, what you can learn from these very interesting, simple objects and fundamental physics processes, which are probably going to be very important for much more complex systems in the future. Thank you very much indeed, Jonathan.